Section: Introduction. In this section, we discuss the capabilities of large language models, LLMs, and their tendency to produce hallucinations, text that sounds coherent but is factually incorrect. This issue limits their use in critical areas like healthcare, where accuracy is essential. Although there has been research on how LLMs recall facts, less attention has been given to understanding why they hallucinate or refuse to answer certain prompts. We recognize that LLMs can hallucinate for various reasons, such as using flawed data or lacking current information. A specific type of hallucination occurs when models are asked about entities they do not know. To explore this, we analyze queries about different types of entities, like movies and cities. When faced with an unknown entity, the model either hallucinates or declines to answer. Our research identifies linear directions in the model's representation space that reflect its self-knowledge, essentially, its ability to assess what it knows or does not know about specific entities. These directions play a crucial role in determining whether the model refuses to answer. However, we note that this self-knowledge may not encompass all forms of self-awareness and could be limited to factual recall. We utilize sparse autoencoders, SAEs, as a tool to uncover these directions. SAEs help us find a clear and interpretable breakdown of model representations, based on the idea that certain properties of the input, like sentiment or truthfulness, are represented as linear directions in the model space. Using GemmaScope, we analyze SAEs trained on various layers of the Gemma 2 models and discover representations of self-knowledge in both the 2B and 9B versions. Our findings reveal that the decision to refuse harmful requests is influenced by a specific direction. We further demonstrate that a model's refusal to answer questions about entity attributes can also be guided by the entity recognition directions we identified. This is particularly interesting because the SAEs were trained on pre-training data, yet the directions derived from them impact knowledge refusal in the chat model, a behavior encouraged during fine-tuning. This supports the idea that fine-tuning often repurposes existing mechanisms. In summary, our contributions include discovering directions in the representation space that indicate whether the model can recall facts about entities, showcasing a form of self-knowledge. We find that these entity recognition directions apply across various types of entities and can influence knowledge refusal in the chat model. By steering these directions, we can prompt the model to hallucinate about unknown entities or refuse to answer questions about known ones. Additionally, we observe that unknown entity recognition directions interfere with the factual recall mechanism by reducing the focus on attribute extraction, which is crucial for accurate responses. We also identify say latents that seem to represent uncertainty and can predict incorrect answers. Section Summary. In this section, we explore how large language models, LLMs, can generate hallucinations, factually incorrect outputs, due to their inability to recognize gaps in their knowledge about various entities. We utilize sparse autoencoders, SAEs, to identify linear directions in the representation space that indicate the model's self-knowledge regarding its factual recall capabilities, demonstrating that these directions can influence the model's decision to refuse or hallucinate when prompted about unknown entities. Section: Steering with say latents. In this section, we discuss how we steer the model using sparse autoencoders, SAEs. We recall that SAEs reconstruct a model's representation by combining decoder latents with a bias. To investigate how language models understand different entities, we created a dataset featuring 4 types of entities: basketball players, movies, cities, and songs, all sourced from Wikidata. For each entity, we gathered relevant attributes and formed templates that include the entity type, name, relation, and attribute. We then prompted the Gemma 2 2B and 9B models to predict attributes based on these templates. We categorized entities as known if the model correctly identified at least 2 attributes, while those it failed to identify were labeled unknown. We used fuzzy string matching to assess correctness and discarded any entities that fell in between. We divided the entities into training, validation, and test sets in a ratio of 50%, 10%, and 40%. We ran the model on prompts containing both known and unknown entities. We focused on the final token's residual stream for known and unknown entities. For each layer, we calculated the activations of each latent in the SE and determined how often each latent was active for known versus unknown entities. We then computed the difference in activity to obtain separation scores for detecting known and unknown entities. Our findings revealed that some SE latents in the training set showed high separation scores, indicating they activated primarily for either known or unknown entities. This pattern was consistent across all entity types, with scores peaking around the 9th layer before leveling off. This suggests that the latents that effectively distinguish between known and unknown entities are located in the middle layers of the model. We also assessed the generality of the latents by measuring their minimum separation scores across the different entity types. A high minimum score indicates robust performance across types, suggesting strong generalization. We observed an increasing trend in these scores, indicating that more generalized latents are concentrated in the intermediate layers. This points to a hierarchical structure in entity representation, with specialized latents in earlier layers and more generalized features emerging in the middle layers. Next, we calculated the minimum separation scores for all SE latents across every layer, ensuring we focused on latents specific to entity tokens by excluding those that activated frequently on random tokens. The latents with the highest minimum separation scores demonstrated the most generalized behavior, which we will analyze further. We also examined the activation patterns of the top known and unknown entity latents, showing their ability to recognize well-known entities and their failure to activate for unrecognized ones. In the following sections, we will explore how these latents impact the model's overall behavior. Section Summary. In this section, we investigate how sparse autoencoders, SAEs, can differentiate between known and unknown entities by analyzing their latent activations across various layers of language models. Our findings reveal that intermediate layers contain latents that effectively generalize across entity types, indicating a hierarchical organization in the model's representation of entities. Section. Entity recognition directions causally affect knowledge refusal. In this section, we define knowledge refusal as the model's choice not to answer a question due to reasons like lacking information or database access, rather than safety issues. To measure knowledge refusals, we adapt factual recall prompts into questions and identify common refusal responses through string matching, such as, "Unfortunately, I don't have access to real-time information." Our model, Gemma 2, includes both a base model and a fine-tuned chat model. We focus on the chat model since it has been specifically tuned for knowledge refusal, which is important for factual accuracy. We hypothesize that entity recognition directions can help chat models induce knowledge refusal. To test this, we use a sample of 100 questions about unknown entities and track how often the model refuses to answer by steering with entity recognition latents. Our findings show that the original model has a certain refusal rate across different entity types. By increasing the activation of known entity latents, we can reduce refusals in 3 entity types. However, increasing unknown entity latents leads to nearly complete refusals. We also examine an orthogonalized model baseline, which involves adjusting weight matrices to ensure they do not contribute to specific directions. This adjustment significantly reduces refusal responses, indicating that these directions are key to the model's knowledge refusal behavior. We analyze the average refusal rate after steering with 10 different random latents, using the same setup as for known and unknown entity latents. Our analysis of the Gemma 2.9b model shows similar trends, though less pronounced than in the 2b model. Next, we explore how entity recognition latents influence the factual recall mechanism. We replicate previous studies on Gemma 2 and find that early attention heads integrate the entity's name into the last token, while later heads extract relevant attributes. We perform activation patching to analyze this, comparing clean runs with known entities to runs with corrupted inputs featuring unknown entities. Our results reveal a significant difference in attention given to known versus unknown entities, with higher attention scores for known entities. We also observe that steering with the top unknown entity latent decreases attention to the last token, while steering with the known entity latent increases attention scores. Our comparisons with random vectors show that steering with known latents enhances attention to entity tokens. Overall, our findings provide strong evidence that entity recognition latents are crucial in regulating the model's attention mechanisms and its ability to extract attributes. Section Summary. In this section, we define knowledge refusal as the model's decision to decline answering questions due to lack of information, and we explore how entity recognition latents influence this behavior by steering the model's attention, revealing that known entities increase attention and reduce refusals, while unknown entities do the opposite. Our findings indicate that manipulating these latents significantly affects the model's factual recall mechanisms and overall knowledge refusal rates. Section. Early entity recognition directions regulate expressing knowledge uncertainty. In this section, we demonstrate that the latent variables related to entity recognition influence how our model expresses uncertainty about its knowledge. We found that while the model implicitly uses its knowledge of recognized entities, it does not explicitly acknowledge this when asked. To explore this, we structured our prompts to adjust the influence of these latent variables. Our results, shown in a figure, reveal that when we guide the model's responses about known entities using unknown entity latents, the difference in responses between yes and no decreases. In contrast, when we guide responses about unknown entities with known entity latents, we see a positive shift in the response difference, indicating that these latents, even slightly, affect how the model expresses uncertainty. Next, we shift our focus to understanding how chat models represent uncertainty, particularly in distinguishing between correct and incorrect answers. We analyze the model's internal representations, specifically looking for signs of uncertainty that might indicate potential errors. We use a dataset of entities, excluding cases where the model refuses to answer, and concentrate on prompts that lead to either correct or incorrect predictions. We hypothesize that the tokens at the end of instructions may summarize the entire question, so we extract representations from the model's residual streams for both types of responses. We aim to identify latent variables that reflect the model's uncertainty when it still attempts to answer, which can lead to incorrect outputs. To do this, we measure the differences in activation levels between correct and incorrect responses using a statistical method that compares the means of two samples. We utilize a pre-trained model for specific layers and focus on the top latents that show the most significant differences in activation. Our findings reveal a clear distinction in activations between correct and incorrect responses, allowing us to classify responses with a high accuracy score. We also observe that the highest scoring latent is associated with uncertainty-related text, further confirming its relevance. Similar patterns of separation between correct and incorrect answers are noted in another model we examined. In terms of related work, we acknowledge recent advancements in understanding how language models recall facts. Key findings include the role of entity tokens and early processing layers in improving accuracy. However, gaps remain in understanding why these models sometimes fail, leading to incorrect outputs. Our research aligns with existing studies on predicting such failures and contributes to the exploration of sparse autoencoders in language model interpretation, highlighting their potential in this area.